Hey, I'm going to do this. This is our third assignment from Unit 9. It's called Conservation of Momentum I. Just kidding, it's a 1, because it's the first of a couple assignments we're going to do with that topic. And it's the first one we're going to do with these, sort of might remind you of LOL diagrams. These are our little momentum conservation diagrams. So I'm just going to jump into this and show you in the context of this problem and the following problems how to use this to keep track of stuff. Alright, we got a railroad yard, train being assembled, empty boxcar coasting at 3 meters per second, strikes a loaded car that's stationary and the cars couple together. Each of the boxcars has a mass of 9,000 kilograms when empty, and the loaded car contains 55,000 kilograms of lumber. Okay, got to read carefully there. So what kind of event is this? This is a collision. We got collisions and explosions. That's what we're going to write here. This is a collision. What objects do I have involved in this? I've got the empty car, and I've got the loaded car. Okay. Initially, the empty car is going at 3 meters per second. And the loaded car is stationary. So the loaded one, this line in the middle is 0, and I have positive and negative here because I can have positive and negative momentum. Depends on the direction. So here the empty car has some momentum. I'm going to give it, it's kind of like LOL diagrams. You got to just decide how much we're going to do. I'm going to give that 2 bars worth. That's like 2 bars in the positive direction for the empty car. And the loaded car doesn't have any because it doesn't have any velocity. Alright? And now the empty car, and the 2 cars stick together. So I should have put that on the same line because they are now stuck together. And so stuck together, they have to have the same amount of momentum. 2 positive blocks worth. Alright. But I should have put that on the same line because they stuck together. So momentum conservation equation. I'm just going to do like this. The initial momentum of the empty one plus the initial momentum of the loaded one equals the final momentum of each one. There's different ways you can write that. You can put more subscripts on there. I'm just going to make this my initial side, my final side. Okay, and then I'm going to start filling stuff in. That's the initial mass times the initial velocity of the empty car. So the empty car has a mass of 9,000 and a velocity of 3. It's fine with me if you leave this out because it's just going to be 0 here because the loaded car does not have any momentum. And then afterwards, I've got 2 empty cars. Each of the boxcars has a mass of 9,000. And the loaded one has this much. So I got 9,000 plus 9,000 plus 55,000. It's 18. Is that going to be 73,000? I think. Hope I did that right. Right, that's 2 boxcars plus that load of lumber. And find the speed of the coupled boxcars. So they're stuck together. That's why I just have one thing there. And then math, or calculator button pushing. 9,000 times 3 divided by 73,000, about 0.37 meters per second. All right. Let's try another one. Astronaut of mass 80 kilograms carries an empty oxygen tank of mass 10 kilograms. By pushing the tank away with a speed of 2 meters per second, the astronaut recoils in the opposite direction. Okay, this is so they're together at the start and then they separate. So that is what we are going to call an explosion. Right, two things together and then something happens and they separate. Okay, so they're not sticking together, so I'm not going to put them on the same line over here. I could put them on the same line here, astronaut plus tank, because they are together here. And they're not moving here, so there's no momentum here, 0. Well, how could there be any momentum here then? Well, the astronaut is going to throw the tank. I imagine throwing the tank in the positive direction, but that's your choice. This is my 0 line here in the middle. And then the astronaut's going to recoil in the other direction because my total here has to equal my total here. And I have 0 total here. So if I have some here on this side, I've got to have the same amount in the other direction so that the total is 0. Right? I hope that makes sense what we're doing with those. Momentum conservation equation. So the momentum of the astronaut plus the tank initially is equal to the momentum of the astronaut plus the momentum of the tank. I can put them together here because they're stuck together. They're holding, the astronaut's holding the tank here. And then here, that's going to be 0 because they ain't moving. And then the momentum of the astronaut is 80 times astronaut's final velocity plus the mass of the tank times 2 meters per second. So imagine that got thrown in the positive direction. So the astronaut, we're expecting to get a negative number there. And sure enough, we do. And you could ask, like, what does this negative sign mean? It means like the other way from the tank. All right. Moving along. A tennis player returns a 30 meter per second serve straight back at 25 meters per second after making contact with the ball for 0.5 seconds. So that's interesting. We're being given a time here, so that's suggesting that we're going to use that impulse momentum. Ball has a mass of 0.2 kilograms. Use momentum conservation to show the change in momentum of the ball. All right. So the two things that are colliding with each other are the ball and the racket, right? So this is a collision. Right, they were not together. If you're thinking, wait, doesn't the ball kind of explode off the racket? We're not going to call that an explosion because they were not together to start with. An explosion is something that starts together as one piece and then breaks into two. So we got the ball. And the racket. I think that's how you spell racket. Is there a C there before the Q? Maybe? I don't know. No spelling test this week. No points off for spelling either. So tennis player returns. So I imagine that the ball's coming like at the player this way, 30 meters per second. That's like the negative direction coming at the player. And then if that's 30, then 25 would be like 2.5 blocks. I'm going to do my best to be faithful to the numbers here. And the racket has to be going the other way, right? So if this is a total, like this is a -3 blocks, and this is 2.5 blocks, I'd have to have -5. So I don't really know exactly what the racket does, but it could be something, I guess it would have to be, maybe I'll make it like this. I'm going to make that 4 blocks. The racket obviously is moving forward, right? And, oh, that couldn't be right, because I have to end up with positives. This is what these diagrams are for. This is a good demonstration of why we're making this. Because I'm going to end up with 2.5 blocks of positives. So this has to be 2.5 blocks bigger than that. And that's if the racket like kind of stops. So let me make this go, let's see, how about 1, 2, 3, 4, 5, 6. I'll make it 6 bigger. And then if this is -3 and this is +6, then the racket's still moving forward, like following through there. Something like that. The important part here is that you show in the diagram that you have the same total amount here as here. So I have -3 and 6, that's a net +3, and then 2.5 and 1/2, that's a net +3. So that could work. The impulse momentum equation is this. So let's see. That would look like, oh, I guess, is that all I'm saying? I guess that's all I want you to write here. And then how much force did the racket exert on the ball? Well, let's see. It's 1/2 second equals the mass of the ball is 0.2. And then the change in velocity is final velocity, which is in the positive direction at 25, minus the initial velocity, which is 30 meters per second in the other direction. That's the #1 mistake that I see, is forgetting that negative sign. So please be careful. I'm going to go over to my calculator and do some button pushing. This is 55 here, 25 plus 30. And then times 0.2, and then divided by 0.5, so I can find the amount of force. It's 22 newtons. So we didn't really have enough information like about the mass of the racket and how fast the racket was going to do an equation, a conservation of momentum equation. So we did that. Just going across the room there to see, on the pacing guide I asked you to do 1 through 3 and then 4 through 6. So I think I'm going to split this into 2 separate videos that go with those 2 parts of the assignment. So see you in a second in another video.